Hello everyone, my name is Lawrence and I'm from Corporate Communication Department of Mimos Berhad. Mimos Berhad is an agency under the Ministry of Science, Technology and Innovation, MOSTI. Mimos is focused on research and development in the E&E sector and ICT. To accomplish this, Mimos engages with the academia, industry and with the government. How are you doing today? I hope everyone is well and excited to join our webinar on surface topography, failure analysis and characterization. In this webinar, the importance of surface topography knowledge in solving typical related issues and suitable analysis techniques will be discussed. The role of material property affecting performance of engineering products will be correlated, and pertinent concept of characterization methods and strategies in failure analysis will be presented. The speaker will highlight the know-how of failure analysis and fundamental concepts needed to resolve the engineering issues. Please note that we will be giving away certificate of attendance to all those who stay with us from the beginning till the end of our webinar. I'll give additional information on this later today. If you have any questions, kindly type it down at the chat section on the YouTube. I'll take these questions up to our presenters. You need to state your name and organization you are representing. With that introduction, allow me to introduce our first speaker, Dr. Shuhairi Saharuddin. Dr. Shuhairi obtained his basic degree in electrical and electronics engineering from University of Strathclyde, Glasgow, Scotland. Following his interest in emerging technologies back then in laser and fiber optics, he further pursued his master's degree in optical electronics in 1992 and established his career path in this field for the following 20 years as a researcher in Sram Berhad and Mimos Berhad. He concluded his academic endeavor in the same field of interest for photonics through doctoral degree in fiber laser research in 2006 from University Putra, Malaysia. He was among the founder of IEEE Photonics Society Malaysia chapter and actively involved as secretary and chairman of the society. His 20 years of R&D experience and skills is now being directed towards activity involving technical problem identification, such as failure analysis process. It currently is established a new interest in spectroscopic methods in failure analysis process, particularly in surface analysis field, PSMB certified trainer. With that introduction, I'll hand this session over to Dr. Shuhairi. Over to you, sir.
Thank you very much, Lawrence, for the kind introduction. Assalamualaikum and salam sejahtera, ladies and gentlemen. My name is Shuhairi, and today I would like to share with you a talk titled Overview of Mimos Failure Analysis Process. And in this presentation, I will give a brief description, very brief description of our failure analysis process that we adopt in Mimos. Allow me to first begin by stressing the importance of failure analysis, both to industry, manufacturers, and also consumer alike. As for manufacturers, it is all about ensuring quality of product, which lead to higher profit margin. And as of for consumers, we are more concerned about the inconvenience caused by substandard products in the market. But there is another important aspect of failure analysis. That is when defect in a product leads to loss of life. As in the case of the defective Takata airbag failure in 2013, which have caused the death of 23 people worldwide, including 7 in Malaysia. So to prevent mishap from happening, a failure analysis process need to take place even before a product reaches its markets. For example, in manufacturing of semiconductor chip, a failure analysis process begin at the very onset of IC design process, fabrication, and up to its packaging processes. An important component of failure analysis process is customer feedbacks. which helps to identify the root cause of product failure. Failure analysis activities play an important role in any investigation of accidents that require explanation on the question of why and how a disaster happened. Now, one example is in the disappearance of a flight MH370, which happened in year 2014. A part of the aircraft wing known as flaperon was found close to an island in the Indian Ocean, and it was analyzed to identify if it belongs to the unfortunate aircraft. Failure analysis engineer perform material analysis on the paint material of the flaperon and compare it with the unique paint material used for the particular aircraft, and in this case MAS Boeing 777 aircraft. And the international team of experts later conclusively confirmed that the flaperon found is indeed from the aircraft flight MH370. Similar forensic approach were adopted in determining the crash of flight MH17 by comparing the paints from the found wreckage with the paint element used in a type of a missile. And in the analysis, it was found that the identified paint matches with the paint of recovered missile parts, which was found inside the aircraft cockpit. And this finding led to a hypothesis by the Dutch Safety Board that the downing of flight MH17 was caused by a missile launched from a BUK surface-to-air missile system. So forensic science and failure analysis resemble very much similar in the sense that it involves a collection of data in order to find the root cause of failure, which help us to plan for corrective action regarding the problem that we are facing. Failure analysis activity in our lab in Mimos mainly involve in electronic components to find the cause of failure in the device. For example, let's have a look on issues that can impair an electronic device such as in IC chip. There are many sections inside the IC chip that can cause defect in its performance, such as in the packaging, the wire bondings, the diametral defects, corrosion, and etc. And defects of this nature may result in condition such as lifted wires in IC, solder void, die crack, short circuit in the IC. Here in Mimos, we adopt a process flow that require the use of several different types of equipment for different analysis, namely in electrical, physical, and material analysis. Sometimes our customer may define equipment or technique that they would prefer to use with the analysis, and in many circumstances, our subject matter experts provide the assistant to make the right choice, and sometimes striking the balance between the cost and the lead time of the service requested. Again, using IC chip with defect as an example, much like a situation when a doctor is presented with a patient symptom, IC failure analysis begins with the narrowing of the possible root cause through validation of symptom using a very basic tools such as a curve tracer, which is a common piece of equipment in semiconductor industry. At this stage, the customer will provide us with symptoms of failure, such as current leakages, open or short circuit for validation. Next, once the symptom has been validated through basic tests, such as in the use of a basic tool like curve tracer, further investigation to locate the suspected cause of symptom will be undertaken. For condition when a structural integrity of a device cannot be compromised, for reasons such as it is an evident in a dispute case, a non-destructive method of defect isolation can be employed, for example using X-ray imaging, and from X-ray imaging we can identify visible faults such as shorting of wires, lifted wires, or even a percentage of voids in BGA balls. Additionally, we can also use 3D X-ray imaging to reconstruct 3D virtual cross-section view inside the failed device without damaging the package. And for situation when internal structure of a device need to be reviewed or exposed for further identification of defects, IC package opening techniques such as wet etching or laser decapsulation will be performed. And sometimes in our lab, we feel that human skill are still needed when it comes to locating a target in a device, which is where the slow process of revealing a defect in IC is necessary. In this case, mechanical polishing, through although crude and time-consuming in its process, but it is very effective when combined with X-ray and 3D X-ray. Another important step or tools in identifying fault in IC packaging is the use of fault localization equipment, such as thermal emission microscope. Again, just like in medicine, when a person needs to be diagnosed for symptom such as cancer, the patient needs to undergo MRI scan, where the possible diagnostic of tumor existence can be ascertained. Similarly, in the case of IC chip, symptom of faulty device presented earlier during electrical verification step can be further elaborated by observing any excessive heating which indicates a high current flow, which may be due to die defects or abnormalities like, for example, dielectric ruptures, metallization, shorts, and also leaky junctions. Of course, fault isolation result will be just an image without much information in it if no action is taken upon it. So the decision of whether you have to go to the operation theater very much depend on the nature of the investigation. And in this case, once we get the permission from our customer, we will basically perform the next level of diagnostic. And for example, we can perform a FIB cut to create shapes that is known as lamella, using focused ion beam to etch or mill specific area in the specimen. The prepared lamella can be then analyzed further by electron microscope, in this case to reveal contact rupture and at the localized area which indicate possible cause of a short circuit. Next is the physical analysis process. This process involves magnifications of features that is hidden from our naked eyes. Basic magnification tools such as digital and laser microscope are common in our analysis, but for higher magnification analysis, electron microscope is employed that can help bring the image up to 1 million times of magnification. For example, this FSM image allows us to magnify a foreign matter hidden inside an IC which otherwise would not be observed under the view of a normal digital microscope. Besides the function to magnify features such as contamination of foreign material, electron microscope also can provide to a certain degree quantitative values such as length and diameters of features under observations. Again, using medicine as an analogy, once tumor is identified through MRI scan, medical doctors need to ascertain whether the tumor is indeed cancerous, and this is done by performing a biopsy. Similarly, once contamination or foreign material are identified in the specimen under study through image magnification at the area of interest using microscopy tool, what other information can we derive or can we obtain next? So this is the stage in our general failure analysis process flow where we hand over the task to our expert in the material failure analysis lab, where they will investigate further and provide quantitative information on types of material found in the specimen. There are various types of spectroscopy equipment which can be used for this purpose. from the simple operation equipment such as Fourier transform infrared spectroscopy, up to the most advanced surface sensitive analytical equipment such as X-ray photoelectron spectroscopy, OJ electron spectroscopy, time of flight secondary ion mass spectroscopy, which can help reveal those atoms that are located near the top surface of a material instead of atoms inside the bulk material, which are much far away from the surface. For example, using a simple FTIR technique for the transform infrared technique, contamination on the surface area of an IC package can be investigated, and through cross-referencing with the FTIR library, we can actually reveal the material under study. So in this case, the material given in the FTIR library indicate that this is the material on the surface of the packaging. A failure of a wire bond with a surface of gold layer due to chlorine and also, in this case, chlorine and also sodium contamination can be identified using equipment such as OJ spectroscopy. And similar situation where the wire failed to bond completely, we can investigate this situation using another spectroscopy equipment such as X-ray photoelectron spectroscopy, which reveal a presence of contamination such as nitrogen and silicon that prevents perfect bonding of wire in this IC chip. In all failure analysis activities in our lab are arranged according to functions of each equipment located in 3 different laboratories, electrical, physical, and also material failure analysis laboratories. And for example, fault isolation equipment such as in thermal emission microscope are located in our electrical failure analysis lab, FISAM in physical failure analysis lab, and XPS in material failure analysis lab. And we have increased our capability in terms of analytical equipment from a mere basic imaging analytical equipment to advanced surface analysis equipment over time. And we are currently having substantial imaging and spectroscopy analytical equipment in our lab. And we are still expanding our capacity to support industry and academia in Malaysia. Early this year, we have acquired several new equipment such as reflective electron energy loss spectroscopy, which provides structural and chemical information of the material studied, and also ion scattering spectroscopy, which characterize the chemical and structural makeup of material, UVS, ultraviolet photoelectron spectroscopy, which determine the molecular orbital energies in valence region. And coming soon, a few more equipment that we have acquired. We'll be receiving more equipment such as variable pressure FISAM, wavelength dispersive X-ray spectroscopy, electron backscatter reflection, etc. The question is, with so many methods and equipment available, which one is the most suitable for your analysis? And as a general rule of thumb, you may ask yourself whether you just need to see features that cause the failure. And in this case, equipment which falls under the category of microscopy is all what you need. You can magnify the image to your liking, and to a certain extent can derive some quantitative information such as thickness and length of the features that you are observing. Or does your analysis require more information related to the type of material existed inside the sample? So in this case, spectroscopy type of analytical equipment would best suit your requirement. So in summary, we have covered a general overview of failure analysis process in our general FA flow, and at each stage there are options in terms of technique or equipment that you can employ for your analytical requirement. And the flow is universal, and it is applicable not only for in semiconductor field but also in material sciences field, In fact, we also received quite a number of samples which are non-semiconductor related. So for those of you who like to know more about our technical capabilities, you might want to directly channel your technical inquiries to our lab director herself, Puan Bazura. And you can also get more information on our pricing scheme for each analytical service offered through Miss Amy, Miss Lachmi Ramasamy. We also, from time to time, conduct public and customized trainings in failure analysis, and you can use this opportunity to expand further your knowledge in this field. And the upcoming training will be on 17 October 2022. You can contact Miss Amy for details of the training. So with that, I urge all of you to get in touch with us for your failure analysis needs. And I hope this short presentation is informative enough for you, and look forward to serving you with our FA service. Thank you very much.
Thank you, Dr. Shuhairi, for that brief overview of what we have here in Mimos. Thank you very much for that wonderful presentation. Ladies and gentlemen, we move on to our second presenter, Professor Engineer Dr. Cheong Kwan Yu, or rather Professor Engineer Dr. Cheong Kwan Yu is a passionate researcher, educator, trainer, consultant, and professional engineer of material science and engineering for more than 20 years. He is a full professor at University of Materials and Mineral Resource Engineering, University Science Malaysia. Professor Chong served as commissioned senior scientist at Korea Electrotechnology Research Institute 2004-2006, adjunct associate professor of Multimedia University Malaysia 2012, visiting lecturer at University Malaysia Perlis 2012, visiting professor at National Taiwan University, Malaysian Semiconductor Technical Advisor, and also worked in NTG Innovation Private Limited Singapore, and the list goes on and on. It's very long and extensive list. Ladies and gentlemen, as a registered professional engineer, board of director, Malaysia, he is also a top research scientist, TRSM in 2013 from Academy of Science Malaysia, and has an accredited and certified professional trainer from the Ministry of Human Resource Malaysia. Professor Chong has delivered more than 300 technical training courses to various local and multinational industries, and has resolved many industry cases related to processing of electronic materials both wafer and package level. With that wonderful resume from Professor, I'd like to introduce Professor back to you. Professor, go ahead.
Thank you very much, Lawrence, for your kind introduction. So ladies and gentlemen, are you able to see my slide right now?
Yes, Professor.
Good, okay. I would like to thank Mimos for giving me this opportunity to share a bit of the philosophy, that I believe in failure analysis and how material engineering, material science can relate to failure analysis and help you to solve your problem. I also like to thank Dr. Suhairi for his wonderful presentation that made my life easier. So at least he provided a big picture to everyone, the components, the process steps, the equipments that used in failure analysis. So my intention here is very simple for this 30 minutes talk. So I just want to bring in the fundamental science, the importance of the hardcore knowledge, basic science to help you to solve your problem. How could this basic science, fundamental science fit into the real application? And why failure analysis activities is strongly relying on the understanding of the science. Definitely choosing a tool is ultimate and very important. Go for you. But end of the day, what is the actual role of this? So, and I also like to bring up failure analysis activities, either the human aspect or the hardcore tools aspect. okay, is something like a football game, okay? So you need a team, you need a team of human being, you need a group of machine in order for you to do the work and achieve your goal. Okay, so I put my presentation as material properties and failure analysis, basically bridging the industry issues and application with engineering knowledge. Okay, so 3 parts. Okay, importance of evidence-based failure analysis, principle of characterization, very brief. Okay, a few slides on that one, and eventually what is the philosophy of one-stop centers here. So basically when you look at characterization, when you look at failure, and when you look at product, and they correlates to each other. So we started with everything in design stage. Okay, you have a computer design, okay, desktop design, okay, paper and pencil design. So everything from the ideas translated into workable design. So during this process, you use a lot of characterization, but this characterization, you don't need to go into the machine and so on. So you yourself, inside your brain, you already processing whether this is right or wrong, and if let's say this happen, what would happen next, and so on. So that is what you are doing inside your brain. We consider that part of the characterization within yourself, and then with the idea, then you come to the material. You put all the material into one product, okay, inside your lab. So from that, you go for a prototype, you go for mass production. Then when you, especially you go for mass production, failures and the failure rate increase significantly, because there are many factors, human factors, machine factors, material factors that come in and contributed to this one. So versus you are in R&D lab, right, well-controlled situation, everything is well known, and the failure would not be that obvious. So, and once you have failure, then you need to go for analysis and find the solution and resolve it. So there are step-by-steps for you to go through in order for you to really stabilize your production and reduce your failure rate. So therefore, we need data to support these processes. Am I right? So, and therefore the data coming from where? The data coming from the characterization. So, and during this process, okay, there are trillions of tools available in the world. Which one is the best to suit your current needs? That is very important. And therefore, not only talking about the data that you have generated from one tools, and end of the day, you have many data generated from multiple tools. How are you going to put together and solve your problem? So therefore, the hardcore consultancy with the knowledge is always needed in order for you to interpret the data, to link the fundamental science with the data, and to see how are you going to propose anything that is reasonable, valid to solve the problem. Okay, so in a high volume manufacturing context, okay, it doesn't matter whether this is a semiconductor, non-semiconductor industry. So if let's say you hit on to the high volume manufacturing, so then basically you are talking about producing something that your customer really needs. Am I right? You need to have your product, you need to have your material, and you need to have your process. If let's say anything happens, so the issues that you are facing, is it because of the product design problem? Is it because of the processing is really out of the window? Or is it really your material is not within the requirement? The incoming material having problems. So end of the day, everything come together and give you the issue. So you as the issue owner, you need to brilliantly differentiate whether which one contributes to what. But in reality, so to high volume manufacturing context, okay, we are talking about high volume manufacturing. We don't talk about R&D, we don't talk about design stage. Okay, so basically, if anything happen, failure usually contributed to material. Okay, I don't believe failure caused by design, because this is high volume manufacturing. I don't believe the issue coming from the process, even though the process contribute a lot. But end of the day, if you have correct material, you should have a correct processing window. If you have a correct material, you process wrongly, is it because of the machine problem or is it because of human problem? Human problem and machine problem are two different things. Am I right? Because human control machine and not machine control human. So therefore, end of the day, still whether any of these giving you the problem, you are selling the tangible product to your customer. Okay, your customer is holding a tangible product that made from material. And when the performance is not following their requirement, they feel unhappy. So meaning that is the hardcore material that give them problem. Am I right? And when you look back, you are looking back the material issue and you are analyzing the material issue. The process is just coming here to change the properties of the material, that the properties can contribute to the application of the product. If the product not working well, the application is out, then basically we say that the material is not able to provide the appropriate properties for the product to work for you. And end of the day, why the material is not working well? So we need to see what contributes to the material failure. Okay, so the failure can be time dependent, the failure can be time independent, depending on how you see it and what you want and so on. So definitely you have different testing in order for you to accelerate the failure. So therefore this is called reliability test. Okay, and there are different failure available in the world. We have very nice failure mode. So from a very small scale to a very large scale. If you are working in semiconductor industry, you're working in car industry, you are working in construction industry. Can you say that, oh, my failure is very exclusive to this particular industry because the failure happening in construction never happens in other industry. My failure happening in LED industry is very exclusive that in photovoltaic industry, they are not happening. So I don't think that this is true and always it is wrong, okay, to make this kind of conclusion. Corrosion happens everywhere. Corrosion happen in construction material, corrosion happen in electronic packaging, corrosion happen in our world. Am I right? So therefore, once you understand the fundamental science of the corrosion, then it can be used to tackle every and any product that relates to corrosion. Example here, peeling off delamination, crack, right? So here to show you that the crack on the wall, what is the difference between this crack on the wall and the crack inside your die, am I right? And you have cracks on the concrete floor, and this is a big scale versus the crack of your thin film. So, and you have these leakages due to diffusion, due to permeability, right? So, and this issue also happens in semiconductor in tiny scale, right? So, voids, pores, pits, roughness, okay, discoloration, and so on and so on. So, all of this to me, right, you need to understand what is the fundamental science that contributed to this. Once you understand that, then you are able to find out the root cause easily, okay? So I don't go into the detail of each of these, but the intention here is just to show you that typical failures happens everywhere, okay? They didn't confined to one industry, okay? So therefore, material failure is what you are looking for, okay? What caused the failure of the material? In order for you to solve the problem, you need to fully understand the background, okay, of the material, what caused the material, what make up of the material, and so on and so on. So therefore, the engineering material field, you are doing failure analysis, you want to find out the root cause. There are steps in order for you to guide yourself towards the root cause. Doesn't matter in your industry, you use what failure mode mechanism and effect analysis or whatever. So basically, end of the day, when you look at this one, you are talking about if let's say the product fail. Okay, the application is not working. Whether the product is big or small, that gives you the failure mode of what skill. So the skill of that will determine end of the day how serious of that particular failure towards the application. And when you say that it is not fulfill your requirement, the properties is up, or what we said in industry is the specification is up. So I want a white LED. Okay, but end of the day, I brought that install, it gives me gray light. So basically the color is up. So customer said that the color is up. Specification by right should be white, and now you give me gray. Then you throw it back to the industry do some analysis. They said that they need to translate the specification into the real properties. Right now, we said that if let's say color is under optical properties. If let's say the on resistance is high, then this is under electrical properties. If let's say the mechanical strength is weak, then it is under mechanical properties. And subsequently, the two speakers will talk about surface topography, and this is under mechanical and structural properties. Okay, so we need to translate this concern into more scientific term in order for us to link this scientific to the fundamental science. So we are going to zoom in how could the properties relates to the fundamental science, which we bring in atom, we bring in electron, we bring in energy, we bring in thermodynamics, we bring in kinetics in order for us to explain why the failure happened. By not doing that one, how are you going to consistently and completely eliminate, okay, the issue, okay, to find out a solution for the issue? That is what we need to nail down to the root cause, and that is the reason why the root come in to address the cause here. Right. So in order for us to go through this process, okay, there are a few things that you need to understand. So not everybody can become a failure analysis engineer. Not everyone can become a problem solver, or not everyone can become a solution finder. So you need to acquire at least 4 of the skill. Definitely, whatever I'm talking about here, you can go to university engineering school to learn that. You can go to science discipline and learn 3 years, 4 years course and to acquire the technical knowledge. However, we also need to know whether you have the intuitive or not. So sometimes you do not have this intuitive. Intuitive is not about looking at the crystal ball, you guess, okay, Magnum 4D. No, we are not talking about that one. So that is part of the training that being brought out when you are young to now. So it is very difficult to train this one. Logical thinking, is it logic to do this? There are sometimes you cannot imagine that people are doing something that is illogic, and it is happening everywhere. So whether it is logic or not, or purposely you do some illogic thing because you design for failure. Some product is designed for failure. You can observe everywhere surrounding you, and you are questioning why this design can become a product. Okay, and professionalism, is it right to do that? Okay, but if you did it, nobody see. If you did it, you are not going to go into Kajang jail. If you did it, nobody is going to catch you. But in reality, if you are doing that, it is not good. So therefore, we call it professionalism. Manipulating data, okay, hiding data. Topography, 2D, 3D. I like to use 3D. I try to tilt, and give you the best angle that I would like to influence the reader. So you as a researcher, you as the engineer, you as a failure analyst, you can manipulate statistical data in order for you to influence the reader if the reader is not well educated. Okay, so therefore, is it right to do that or not? Okay, so therefore, to me, the first part, you can go to the school, you can learn, but the rest here is very, very difficult. Okay, so is the failure of your product is so exclusive and unique that a special skill and knowledge are needed in order for you to solve the problem? So therefore, you need to ask this question. If let's say you work in industry A, you need to learn that particular skill. B, C, D, E, F, G. End of the day, even though lifelong learning is good, but you cannot blend the knowledge together. You cannot integrate the knowledge together. Very important. If based on this, you ask yourself, daily life and your working life. If let's say you cannot integrate them, you cannot blend them together, then you have the problem that you are seeing right now. So whatever you see in your daily life, you can solve using scientific knowledge in your industry. Definitely you are able to do that perfectly. Okay, you ask yourself why sky is blue. Okay, why the color is like this, why it is so weak, why my paint from the wall always come down, am I peeling off, why this material cannot withstand high temperature, why all my plastic product that exposed to the environment, easy to degrade, change color, and so on. So everything can be easily explained by using fundamental science, and these are the typical problems that you are facing in your industry product as well. So therefore, we would like to introduce one we call generalizing approach in order for you to find the root cause of the problem. So you need to everything boil down to a very easy manner that you can use the fundamental science to explain. If when you boil down to a very simple block diagram and you cannot find a science principle law to explain that one, basically you cannot move on. You also cannot identify which is the correct tools in order for you to move on. So therefore, this is the first step that you need to do. A big picture, I give you this few words, I put it into a big picture, and this big picture may scare you away. So don't worry, one by one. Okay. So basically you have a material. The material need to be processed accordingly. So when you process the material, basically you try to input energy, you try to input the environment, you try to input the time, only these three. Okay, environment, energy, time, in order for you to interact with the material so that you are able to change the structure composition, the structure related to the crystallinity, the structure related to morphology, the structure related to the topography, and the topography will be the goal of the subsequent talk, right? And whatever you are doing, you need to make sure that the uniformity of those would be there. Whether the roughness is the same, flatness is the same across the material. And end of the day, what is the dimension geometry that you are processing? You process a big wide area versus a small pieces of material. The processing condition would be different. It can be done in the small pieces of area. Doesn't mean that this process can be upscale to a larger area. So therefore, scale geometry is very important. End of the day, when you do the processing towards the material, you are going to change the characteristic behavior, or we call properties of the material, either in mechanical, thermal, and so on. So what are the properties that you would like the material, end of the day, to showcase? The showcase of the properties would be the properties that your customer is going to use. I always say that the car not necessarily need to make of a steel, metal, and so on. If you can use a piece of leaf to make the car, the important thing here is the process can be used to convert the leaf into the strength as strong as a piece of metal. You go ahead and use a piece of leaf. So therefore, the processing is very, very important, whether you are able to convert it to what? If you are not able to control this one, end of the day, you are going to have a problem. So what are the problem? When you produce this through the process, you get the product out, and the product come with certain performance that your customer already defined. Okay, you can define whatever under the sun, but end of the day, your customer dislike it, doesn't matter, right? End of the day, you cannot get the product out, your customer don't buy it, and so on. So definitely your customer say that, okay, you promise white light, you give me gray light, I'm not happy. You say that this is hard, but end of the day, it is soft. So therefore, issues come in. So issues, is it because of time zero, time dependence? In the world, there are only two root cause of the issue. One, the root cause is caused by residual stress. The other one is caused by contamination. Any other of the subsequent one actually originated from these two, okay? And end of the day, whether you say that it is caused by A, caused by B, caused by C, is it really caused by residual stress? We need to do a lot of characterization. So in order for us to really find out, oh, actually whatever properties that I am seeing right now is actually not matching with the properties that you are producing in your factory. So at end of the day, in order for us to rectify the issue, we need to go for other processes to rescue back, okay, to really suppress the issue and bring back the properties that we want. So this can be done in your industry, be part of the subsequent process. So therefore, sometimes you have produced certain things. After that, you go for post-process, or we call heat treatment, post-deposition treatment, and so on and so on. So this is the case that we are talking about. So in order for you to say that after I have done the complete processing to rectify, to reduce the stress, to reduce the contamination, then it is ready for application, right? So, and when your customer receive this one, the customer is going to make complaint also if, let's say, the product fail, okay, within the warranty period. You promise 2 years, it fails 2 months. And why? Then you need to look at the extrinsic factor that contributes to the issue. Extrinsic factor, basically you look at what are the energy that being absorbed by the product. End of the day, fail a specific material. So it can come from hygroscopic, chemical, thermomechanical, electrical, mechanical, chemical, optical, electromagnetic radiation, and so on and so on. Okay, so and definitely when you looking at these fundamental science behind, you also need to consider economic aspect and sustainability. Sustainability, basically, when you use the material, when you use the process, is it safe? Is it green? Is it sustainable enough for our future? Economic material, is it very expensive? If this is expensive, are you able to judge the usage of this one? Maybe this is better in long run. Okay, maybe the value that you are getting is much better than that, and so on. So characterization. Does it mean that you pay higher price, you are going to get better return? Am I right? Sometimes it's not. You pay higher price, not necessarily you get better return. So whether the money that you spend, is it good enough for you to get the value out? So that is basically the economic part of that one. So, and looking at this one, I put down there are 8 factors that contributed to this, like what we explained, 1, 2, 3, 4. I put down the number here briefly. So this is the fundamental knowledge that you need to acquire. Why? Because this is all related to material that end of the day will go into your product. Whether this is a glove, semiconductor, a car, a tire, a chemical product, a steel bar, doesn't matter. So, and as an example, if let's say this is a semiconductor product, what material that you need to put in? Should I use silicon? Should I use silicon carbide? Should I use gallium nitride? Should I use epoxy, or should I use silicon? Am I right? So there are trillion of material available in the world. Why I should use this material and not the other material? So therefore, the selection is based on the 8 things: structure, process, performance, properties, characterization, economy, skill, and dimension, as well as the sustainability concept. So these are the fundamental knowledge that serve as a backbone to support your material. Meaning that if, let's say, you have problem, am I right? You want to solve material related problem, you need to revisit back this one. You want to change, you want to improve your process, increase the yield, continuous quality improvement activity, you need to look back to this one, okay? It's not independent, the 8 of those, they are integrated together. And this, I put that as a fundamental knowledge. By looking at this fundamental knowledge, this doesn't guarantee you are able to solve your problem. You need to have another piece of knowledge called technological knowledge. Technological knowledge, for example, you have a power device. Okay, so power device is not working because the forward bias is too high, because the on resistance is too high. The steel bar is not strong enough, it is weak. Is it because of what? So definitely material, but you need to know how does the product being used. If this is used in biomedical product, am I right? So you need to understand how the material actually end up to the body. Is there any interaction between the medicine, the fluid, the blood with the material surface? How to resolve this problem? How to increase the hydrophobicity, hydrophilicity of those, am I right? So therefore, technological knowledge in terms of application need to link it to the fundamental science. Okay, that is what is important. Okay, so basically, what is your problem? You are the owner of your problem. You should be able to identify. You should be able to go forward to that. Differentiate between R&D work and failure analysis work. So basically, we need to know that these are totally two different perspectives. So before we go into R&D and FA, look at this one. We basically want to know and unknown. So I'm not sure whether you know whether I'm wearing trousers or blouse or not. So you only can see from the top. So if you cannot see my bottom, then you started to guess. So if you have something that is unknown, where R&D activity and FA activities is actually trying to find the unknown, you are going to look for three things: what, how many, and where. What is the chemical composition? Am I wearing trousers, pants, or am I wearing a short? What chemical? So is this silicon carbide, gallium nitride? Is it TiO2 or what? How many concentration, part per million, part per trillion, 1 atomic percent? Where is it on the surface, inside the interface, deep inside the bulk? So these are the things that you want to find out the information. Human is very simple. You do not know, you ask. Am I right? So that is the activities of teaching and learning. So therefore, you ask for what? To find answer. However, material is dead wood. You cannot ask the material, how are you? Is it wearing blouse or are you wearing pants? Okay, how old are you? They cannot answer to you. In order for you to get this information, you have to do characterization and talk to the dead wood. So sorry about that, almost 30 minutes already. R&D work, basically what you are doing, A plus B, you want to find out C. In this activity, you know what A, you know what B, because you put in and eventually you create C. You try to characterize C. In FA, A plus B becomes C. You see the C in front of you. You want to find C, but you do not know what is A, you do not know what is B. So once you find C, in order for you to know what is A and B, you try to do some prediction. You try to bring in theory. You try to reinvent the wheel and so on. So therefore, for R&D, it is very straightforward, simple, because they are working in well-controlled environment. You only need to look at C only. But for FA, you need to know everything. Am I right? It's very simple, straightforward. I put down in one slide. So meaning that you need to do systematic activities to find out the evidence. Okay. So and therefore characterization come in to find out the evidence. With the evidence, it links to the solution. Seeing is believing. Okay. But basically, we are not saying that definitely you need to see the image and so on. Seeing the data is also another approach. So failure analysis basically is a CSI activities. Are you finding the best technique to solve your problem? Always we want to find a best technique. Unfortunately, we do not have the best technique. Okay, we have the appropriate technique for this particular case. If let's say all the cases can use the same strategy, end of the day, this is not FA work anymore. So you keep on repeating the failure. You keep on repeating the same strategy to solve the problem. Basically, you don't solve the problem. Am I right? Why? Because the issue repeated. Coming back to the same premise, to the same owner. So there are many techniques available. So I put down in this analogy comparison. Okay, so depending on the transportation, you have a low end, you have a high end one. So always we say that, can we get a cheapest, fastest, most reliable technique to solve my problem? So end of the day, the answer is no. So you need to have a combination. You need to have a team of equipment in order for you to find out the root cause, especially those are very, very complicated one. I skip this one due to limitation of time. So basically, systematic material failure analysis, we are talking about 3C. Create, challenge, confirm. Create. What is your storyline? Tell me, what make you think that this caused the failure? You tell me the story. Who is the main actor? Who is the supporting actor? Okay. End of the day, what will happen? You tell me this, and you have the postulation, and you assume this happened, and so on. Good. I'm going to verify whether this is true or not. So verification is characterization. Verification is to challenge whatever you mentioned just now in the story, in your movie, in your dream. So this is daydreaming. To verify, you need to do a lot of characterization. Either you look at the real actual sample, you go to lab, you try to modify and you create the samples. So therefore, this is to challenge your storyline. At the end of the day, based on this one, data came out and so on, then you try to interpret, analyze in order for you to confirm whether this is the root cause, and the root cause must base on the theory. The theory is what we call hypothesis. So therefore, the mechanism that the industry always like to learn, am I right? The mechanism can be used to explain this failure. This mechanism doesn't mean that it can explain your problem. So therefore, in order for us to see that the current available theory of mechanism can use to explain your failure, you need to go back to your storyline. You need to go back to the verification process, where verification is actually the principle of getting information from the material, where you are saying that these are the unknown. If human and human, you do communication. If human and dead wood with material, with your product, we call this as characterization. You need to use a proper skill. You need to know what is your intention of doing that one, okay, to find out what you want. So I want to find out chemical information, or I want to find out the structural information, or I want to find out the thermal information. There are different types of characterization available in the world. It can be classified according to this pyramid, whether this is R&D tools, or this is belonging to FA tools, or this is a QA QC tools. If you are having a QA QC tools, for example, XRF to measure the film thickness, coating thickness in factory, that cannot be used as an R&D tool. Okay, so you cannot convert this into this direction, but whatever here, you can use it at the towards down here. Okay, so I hope you understand this hierarchy. So topography, I leave it to your friends. Okay, there are two speakers that going to talk about topography. Okay, I skip that. There are technique, for example, stylus profiler, SPM, AFM, interferometry, white light interferometry, okay, confocal laser microscope that can be used to define the topography. Maybe later you can ask them what is the differences between topography and morphology, and each of these come with different advantages and disadvantages, right? So, and basically, what we would like to offer you here is definitely you have problem, you talk to us, we suggest, we propose what are the most appropriate characterization method and strategy that we can offer. And once the data came out, then we said that, okay, we try to help you to analyze it as well as propose certain root causes by providing some consultancy service to you. Okay, so you can talk to Mimos to get more information related to these one-stop centers. With this, I thank you for your attention, and sorry about that. I think 5 or 10 minutes behind time. Thank you very much. I pass it back to you, Lawrence.
Thank you, Professor. I mean, your presentation was superb. You had really touched a lot of subjects that many people were interested to know. Thank you, Professor, for this wonderful sharing. Next, we move on to our third speaker, Ms. Hasniza Hashim. She received a Bachelor's of Engineering in Electrical and Electronics Engineering from University of Plymouth, United Kingdom in 1997. She has almost 25 years of combination work experience in failure analysis and product engineering. She is the lab head for failure analysis, which consists of physical and electrical analysis lab. A team provides immediate support to industries and universities for equipment services in field emission, scanning, electron microscope, energy repulsive spectrography, wow, that's a mouthful, Nano Indenter, atomic force microscopy, photon and thermal emission microscope, X-ray, 2D, 3D X-ray, as well as destructive testing such as mechanical polishing and package decapsulation. She has conducted a series of technical training for students and engineering from the industries on the operations, techniques, and application of the FESEM, EDS, and Nano Indenter. She's also the ISO IEC 17025 approved signatory for EDS and physical dimension measurement in micro and nano scale, PSMB certified trainer. So she's a great person with full of resource knowledge. So with that introduction, I'll hand you over to Ms. Hasniza. Go ahead, Ms. Hasniza.
Thank you very much, Lawrence, for your brief introductions. Okay. Can you see my slides? Okay. Okay. Thank you very much for all for attending this webinar. Okay. This is the outline. Today, first of all, let me introduce today I'm going to talk about the mechanical testing using the nano indentation technique. These are the outlines for today's presentation. I will talk about a little bit about the traditional mechanical testing review, and then I move on to why we need the nano indentation testings. And I also will talk about the equipment that we have in our labs and also some of the factors that can, in terms of sample preparation, that can help us to get good data, and also some of the case studies related with the nano indentation testing. First of all, like let's look at the traditional methods of doing the mechanical testings. When we want to get the hardness or modulus of certain material, we normally tend to use the micro hardness testing. Okay. So, when we talk about the scale of testing, if we do the micro hardness test, we enter the micro regime of testing, but we still does not quite reach the nanoscale in terms of mechanical testing. So, as an example, this is a composite material that was tested using the viscous micro hardness test, which the indent must be large enough to be inspected using the optical microscope. We can clearly see from these indentations that both the filler and base material were indented, or in other words, the bulk of material was tested. So if this happens, then if let's say we want to know the hardness of the top layers, we didn't achieve the intention, then we need to have another method to get the better result compared with by using better techniques. So why do we need the nano indentation? The primary objective of using the nano indentation is to measure the mechanical properties of material, where the size or precise location are limiting factors. So as example here, if let's say you have a very thin layers and you want to know the hardness and modulus of the top layer, we need to have the instrument that can control the depth of the penetration of a thin film. We must take care when indenting a thin film to avoid also testing the properties of underlying layers. Another reason to the nanomechanical testing is to test at a very specific sites with very fine precision and control. So it only can be done if you do the testing using the nano indentation techniques. So, what is actually the nano indenter? A nano indenter is the main component of indentation hardness test that used in nano indentations. Since the mid-1970s, nano indentation became the primary method of measuring and testing very small volumes of mechanical properties. Nano indentation will give the very localized hardness, whereas micro indentation gives the average hardness over a large area. For example, nano indentation gives the hardness within the grains, while micro hardness is average value of different grains. And the tip of the indenter can be made of sharp, flat, or rounded to a cylindrical or spherical shape, and normally made by diamond or sapphire. There are many types of nano indenters in current use, differing many on their tip geometry. In our lab, we are using the Berkovich tips. Here are a lot of specifications about our instrument, which is the Bruker Hycitron TI-950 Tribord Indenter. The system comes with a dual testing capability, meaning that it will provide an available force ranging from 13 nanonewton up to 10 Newton. We have two types of transducer. We have what we call it 2D transducer, and also we have this 3D omniprobe transducer. For this 2D transducer, it has the maximum force up to, we can apply the maximum force up to 10 milliliters and the maximum displacement up to 5 microns. So it's really true nano indentation testing. For the omniprobe, it can achieve, we can apply force up to 10 newtons and the displacement can be up to 80 microns. This is what we call it the nano indentation to micro indentation testing. For this 2D transducer, the probe also can be used as a contact mode scanning probe microscope or SPM. There are piezo actuators which can scan the probe at low force around 2 micronewton along the surface, rastering and measuring the displacement of the probe constantly. From that, it can give you a spatial representation and a 3D dimensional value. So basically you get a topographical map of the area that you want to scan. The SPM method is actually very important for many users as it can help get an approximate value of the roughness of the sample surface before we do the indentations. It can also aid in selecting a very specific area of testing. And it also can also help by imaging the residual indent to be confirmed or even quantify its quality. The system also comes with a pretty good optical microscope, which is mostly used to navigate the sample. Now, let's look how the force is actually applied and how displacement is measured. In our system, the probe is installed into the floating metal plate of 3-plate capacitive transducer. The displacement is measured by running two AC 180 degrees out of phase of each other to the top and bottom of the 3-plate capacitive sensor. The AC signals are observed by the center plate and the sum of the signal corresponds to a measured displacement. To apply load, a DC offset is applied to the lower plate of the transducer that electrostatically attracts the center plate downward. These are the means estimate available on our Bruker TI-950 test. We have this quasi-static nano indentation where most of the people just refer to as a nano indentations. Most commonly, the commonly properties measured through nano indentations are elastic modulus and hardness. However, the technique can also be used to extract other informations like fracture toughness or other mechanical properties. There is also a scratch testing mode which can be used to determine the properties like coefficient of frictions or adhesion properties of film substrate if you have a delamination, if you have failures like delaminations. There is another mode also called accelerated property mapping, which is basically a rapid-fire nano indentation experiment, while as compared with the quasi-static nano indentation, where it's generally on time scale of many seconds up to minutes. The XPM modes, however, does hundreds of indents in a matter of seconds over a large area, which is a lot of data over a pretty large area. And this can be used to make a map relative to modulus and hardness. Like you can see here, we have indents about 16 micro square area, and we assign a color map was on low hardness to high hardness. So in this case, yellow and orange hardness represent the lower hardness, and the blue is represent the higher hardness. So you can get the idea of the distribution of the hardness on your material. The system also, as I mentioned before, the system also equipped with in-situ imaging. It used the indenter tip for nanometer precision test positioning and surface topography information. In the next following slide, I will show you the benefit of having in-situ imaging in our system. So this is the image taken from the optical microscope. Example, like if you want to do the indentation at this area, because it's a very nano indentation, we can specify the location of your indentation. And then after that, if you want to know whether you have indent at a correct location, you have to go to another tools to do the inspection. So in the past, people had to go back and forth between SEM and the Nano Indenter to confirm the correct placement of very small nano indentation, which is a very time-consuming process. However, with the in-situ imaging, we can locate the area where we want to do the indentations by using the optical microscope. Then we are using the SPM to do the imaging before we do the indentations. And then after that, once we do the indentation, we can also do re-image the area of indentation so that we can check the quality of indentation, whether we have done the indentation at the correct way, at the correct place. Now I would like to explain a little bit about the theory of the nano indentation. With a nano indentation, a probe of a known shape or geometry and material properties, like this, a diamond probe, is pushed into a material while continuously monitor force and displacement. During indentation, the vertical displacement of probe is measured during control loading and unloading phases. Typically, there is some some period of holding tip in the place at max load and max this depth for some time, which we also call dwell period. There are a variety of probe geometries exist, depends on the application. As I mentioned just now, our lab, we are using the Berkovich probe because it has 3 sides and as the 3 sides do naturally sharpen to a point. Also commonly used is corner spherical probe. This probe is used for scratch testing, also for indentation of soft materials. So when we talk about the indentation, we also need to at least have an information about deformation during the indentation. So for the first first deformation, the elastic deformation occurs when the displacement of material is totally recovered after forces applied, meaning that the loading curve and the unloading curve would essentially perfectly overlap, like here. If the material remains permanently deformed after a load is applied, it's called plastic deformation, meaning you would have a loading phase and then a straight down drop for the unloading phase. In nano indentation, we are hoping to see something in the middle of two called either electroplastic or inelastic deformations. For our system, we are actually using the Oliver Farr method. Actually, there are many kinds of methods that can use to generate hardness and modulus, but in our system, we are using the Oliver and Farr methods. So before I go to how we can get the modulus and hardness calculated from the unloading curve, I need to introduce some important terms. This is the cross section of indentation area. The initial surface of the sample before the tip approach is indicated by these red lines. The indenter profile is shown here as the blue lines. And the maximum depth that the tip reaches from the initial sample surface is considered the penetration depth, which sometimes we also call H or H max. So that would simply be the initial surface being near zero, and then wherever the tips reach being the maximum depth. So just now we have do the indentation. Now from the indentation testing, we have this force and displacement curve. This is force and displacement curve from a single indent on fused quartz. As you can see here, the slope of the loading curve has a parabolic shape since the contact area between the probe and the sample increase as a square of displacement into a sample. Thus, more force is required to displace the probe into the sample. As one can see here, this loading curve is not lined up with unloading curve. During loading, the plastic and elastic deformation occurs. Upon unloading, the plastic deformation is stored and the stored elastic energy is recovered. So first, we need to calculate the stiffness of the material. The stiffness is simply the slope fit of the unloaded curve at max load. So from this equation, the contact depth is then calculated as follows. HC, the contact depth, is equal to the max depth minus the max force times epsilon, which is some geometric constant depending on the indenter chip installed, divided by the stiffness. The modulus measured in nano indentation is specifically called reduced modulus, or we call it ER. The relationship between reduced modulus and a Poisson ratio of our indenter, in our case, is our diamond probe, and unknown modulus and unknown Poisson ratio of a sample is shown via this expression. In actual nano indentation experiment, we can calculate modulus and hardness based on stiffness and contact area at the maximum force. So reduced modulus would simply be half of the square root of pi times the measured stiffness divided by the square root of the projected contact area. And then the hardness is simply equal to the max force during the experiment divided by the projected contact area. As you can see here from the two formulas, the projected contact area is plugged into the formula which calculates the modulus and hardness. It is very important to determine the tip area function in advance before we can do the testings. In order to determine the contact area function, we usually perform indentation using fused quartz sample whose elastic modulus and Poisson ratios are 69.9 gigapascal and 0.7 respectively. So what we do here is we did a series of indents at various contact depth, varying normal loads are performed on fused quartz, and then the contact area and contact depth is calculated. By calculating the projected area as function of contact depth to known samples, we can then apply to unknown samples to determine the modulus and hardness. In this slide, I show you the data analysis software looks like after you have loaded a force displacement curve from the Nano Indentation experiment. Now we have this force displacement curve. What we can do is we can click on the execute fit button, and then the software will automatically pulse a store tip area, then calculates the maximum force. It also detects the unloading curve, measure the slope. This one measure the slope, and then calculates the projected contact area. And then, of course, with all this information being pulled, it gives you the values of hardness and modulus here at the top. Well, that wraps up all the background theory that I have for this presentation. Okay, before we want to do the indentation, we need to specify the following characteristics of the sample. We need to know, if possible, we need to know the material of the sample for testing. We need to know the size of the sample. Also, it's very important if you can know the surface roughness of the sample before we do the indentation, and also the thickness of the layer. If the intention of our testing is to measure the top layer, the material properties of the top layer. The sample for testing should be well prepared. The sample should be flat and should be parallel with the bottom part of the sample. To achieve this, we can do by preparing the sample with a method like do the parallel cutting of both top and bottom surface. After that, we clean and we pressurize air or washing in alcohol and ultrasonic bath, and then do the fine polishing. And also it's advisable to inspect the surface of the sample using either optical microscope or Afm or in situ imaging, especially for measuring the surface roughness. After that, we need to mount the sample on the sample stage. Like most analytical techniques, you set yourself up for success and failure by just how you prepare your sample. As I mentioned before, we need the sample to be flat, smooth, and secure as possible for nano indentation, because the testing is in nano scale, so any variation can cause can affect a lot in the testing results. There are several ways to mount the samples. We can mount the sample onto a magnetic Afm specimen disc as here, and then we can put on our magnetic sample stage, or we can use the suction ring to hold on a very smooth sample like glass slide or clean wafer, or if you have like a flexible or odd-shaped samples like bone or fiber sample, you probably need to embed it in some resin or epoxy and do the cross-section and polish the surface down as shown here. Obviously, after that, you need to use some sort of like super glue to fix your sample on your, whether your magnetic metal disc or on your clean surface or your clean wafer. However, please take into consideration that once we apply the super glue, the sample cannot be testing anymore for if let's say you want to do other testing, because when it's super glue, it's very hard to remove from the metal plate or from the glass slide or from the wafers that we put the samples. So these are a quick snapshot of the wide range of application that nanomechanical testing can be applied. We can apply the nano indentation techniques on ceramic, protective coating, ceramic composite, thin films, metal to check for the individual grains, metafilm. Also, we can use on the polymer, and also on the biological materials such as bone, seeds, and so on. And also, it depends on the probe availability in the lab. Now, I would like to show you some of the case studies using our TI 950 Tribal Indenter. We are using two types of probe, which is 2D transducer and 3D omni probe. Okay, this is the objective of this testing is to extract the hardness and modulus from the silicon wafer. So the analysis required to do the indentation at the center and the edge of the samples. So what we do is we are using the 2D transducer probe. We apply the force of 10 millinewton with loading unloading segment time of 5 seconds with the hold time of 2 seconds. So after before we do the indentation, we have already do the scanning on the area to be indented. And from this in situ image, we can see that there's a very fine smooth, and this is meets the requirement for do the nano indentations. So once we do the nano indentation, we can capture the image using the in situ imaging, where we can see the topography of the indentation and also the 3D profile. And it comes out with the result of modulus and hardness. So from these samples, we can see that both the center and left area of the wafers produce almost the same result. For the next case is the hardness and reduced modulus of the position layer at different thickness layer. I'm sorry, the objective is to get the hardness and reduce modulus on the position layer with the same thickness layer but different material. It also used the nano indentation technique at the center and edge of the sample by also using the standard 2D transducer. We also apply up to 10 millinewton with the unloading and loading time of 5 seconds and hold time of 2 seconds. So from this in situ imaging, we can see that there's two types of material surface that can be observed through the in situ imaging techniques. So this is the result at the center of the wafers. So one of them for the sample AH produced a modulus of 180.84 gigapascal, and the hardness around is 21.15 gigapascal. By the sample B, the modulus is 75.6 gigapascal and 8.05 gigapascal. Same goes with the result at the edge of the wafer. And when we plotted the histogram, we can see that the hardness and modulus of the sample A at the center and edge is higher as compared with the hardness and modulus of sample B, even though the thickness of the layer is the same, which is 0.5 microns. We apply the same force to both sample. Another study is we did the testing on a Xerox sample. Okay, for this one, we are not using the 2D transducer. Instead, we are using the 3D omniprobe because the sample surface is quite rough. And then the testing requirements is the force that we apply is more than what can be offered for 2D transducer. So for these samples, since this is a bulk analysis, it requires the force to be applied of 450 millionewton, and the loading curve and the loading and unloading time we set at 5 seconds. With the whole time we increase to 15 seconds. So because this is we are doing the indentations at the same area, and since the surface of the sample is flat, we can generate many informations using the grid techniques. Means that we can do the indentation with a total of 18 indentation, means that we can do 6 rows and 3 columns to get more data. So this is the example of the result that can be generated from the testing. So if we have many data, we can have more clear pictures on the distribution of the hardness or modulus on your sample. This is the image taken using the optical microscope image. Take note that this image can be visible via the optical microscope if the force that we applied is quite high. Otherwise, we can't see this image through optical microscope. So we also can, from the result, we can also plot the pH curve and also we can plot the hardness versus radius modulus graphs to see the distribution, or also see if there is some outliers of the data from out of the 13 indenter that we have performed. For the next testing is we did the indentation on the PCB boards. So this is what I want to show you the capability of the in situ imaging. It's not just give the topography images, but it also can give the 3D images so that we can get the better understanding of the indentation and also the conditions of surface after do the indentation, whether there is some fracture after we did the indentation. And also there's a profiler that we can measure the vertical and horizontal of the indentations. And this is another example of we did the indentation on the tip samples. So as you can see here, the surface of the tip is not really flat, but there's some area that flat. So what we have to do is that we have to put some resins at the bottom of the sample to make sure that the sample is not moved. Then after that, we use the super glue to paste the samples onto the clean wafer, and then use the vacuum chuck to hold the sample. And then we do the indentations on the surface of the polymer coating on the tip. And we get this pH curve as a comparison. And these are the data, the reduced modulus and hardness produced from the indentation using the 3D OmniProbe. When we are using the 3D OmniProbe, we can only depend on the optical microscope to get the image before and after indentations. Last but not least, this is the accelerated property mapping. So when we apply when we want to do the XPM testing, we need to use these only trapezoid load functions, and then we need to set how many indentation that we want to do. Example, for this one, I want it to do 20 by 20 with the spacing between each indent is 1.5 microns. So a total of 400 indentation will be performed, with the maximum force that we apply will be up to 300 micronewton. So this is the image that been captured by in situ imaging. This is what I just now is rapid fire testing. We can do this 400 indents within a seconds, and then it comes with this mapping where we can see the distribution of the hardness and modulus. Example, like here, most the chart give different colors for the different hardness and modulus, and also it comes with the distribution chart as well. Okay, with that, end my presentation for the nanomechanical testings through nano indentation techniques. If you have any question, you can email to me through my email address here.
On Asnisa, there's a question for you here from YouTube.
Okay.
It's about thin film analysis.
Okay.
Could you please explain some background or purpose of this analysis? What instrument have been used for this thin film analysis? From Nur Amira.
Okay. Thank you very much for the questions. Okay, as I mentioned just now, let me go back. Okay, I give you this example. For the thin film analysis, let's say that if you have your layer of film is around 1 micron, or maybe I give you about 0.5 micron. So the first thing that we need to do is to check how many the force that can be applied to the samples by doing the multiple load indentations. This purpose is to make sure that the load that we apply is not hitting the next subsequent layer, because the layer is very thin. So it's very important to make sure that the probe is not hitting the next layer. So how we do it is that we are using this 2D transducer, because this 2D transducer has the limitations of penetration depth up to 5 microns. So it means that if, let's say, your layers is if let's say the force we apply is more than 5 micron, the system automatically will withdraw from the sample. So and then the system also have we call it a depth control method, where we need to control the penetration depth. If let's say your thin film is 0.5, it's better for us to do the indentation up to around 100 nanometer, so that it's really between the center of your film thickness, rather than hitting the next subsequent layer. So we still use on the question what instrument we use for this thin film analysis. We use this nano indentation, our system, which is our TI 950 travel indenter, but we use the 2D transducer instead. Is it answering your questions?
I hope what Nur Amira, that explanation from Wan Hasniza has cleared your mind. Is there any other questions? Otherwise, we'll move on to the next speaker. Any more questions? Okay, there's no questions. Perhaps there may be questions at the end. So thank you, Puan, for your explanation. And we move on to the next speaker. Thank you, Puan.
Thank you, Lawrence.
Our final speaker for today is Mr. Brian Lim. Mr. Brian Lim is the Application Manager at Park Systems Singapore, where he supports customer demo requests and application modes training. He is also holding the Service Manager's position with more than 10 years of AFM experience in service and application support. For customers, Brian is well versed in various application modes like electrical, nanomechanical, magnetic, and fluid imaging modes in different research fields. With that, over to you, Mr. Brian.
Thank you, Lawrence, for the introduction. So good morning to everyone.
Good morning.
Let me share the PPT. All right, can you all see my screen? All right, okay, so today I'm going to talk to you about the atomic force microscope applications in the industrial sector. Okay, so first I'll go through what is an AFM, and then follow on by some of the failure analysis and characterization applications in the industry. So these are some of the various modes of the AFM which can do. And then follow on, I'll talk about the Park AFM technology. Since I'm working for Park Systems, I'll talk about some of the technology of the Park AFM, and I'll give a summary, overall summary. Okay, so what is an atomic force microscope? So typically when we think of a microscope, we think about optical or electron microscope. And so a simple question is, can a microscope give you a 3D information? Right, so this is before that was this is an optical microscope, and this is electron microscope. So the answer is it depends. It depends on what kind of microscope. So this slide will show all the different techniques for measuring the surface morphology. And for some microscope like SEM, you cannot have a Z information, depth information. Optical microscope, you also cannot have any Z information, which means you cannot have a 3D profile. However, for AFM, you can have a 3D profile. And it's also very easy to use. You can use in air, liquid, vacuum, but for SEM, you can only use it in vacuum environment. Okay, so the magnification value of AFM is also one of the most highest. Okay, so what is a real-life AFM example? So the closest example I can think of is our finger. So our finger, when we move across a rough surface, we can feel that it's rough. Or when we move our finger across a smooth surface, like a mirror, we can feel it's smooth. So basically, our brain is like the AFM controller, which can distinguish between whether the surface is rough or smooth. Okay, so but in AFM, we don't use a finger, we use the Afm Cantilever. So Afm Cantilever is a fabricated cantilever from most of the time it's silicon nitride material, and it has a very sharp tip at the end. So the AFM, it needs to have a feedback. So it uses a laser, which falls on the cantilever end, and it goes back to a photosensitive photodetector. This will actually detect whether the tip is pushed up or it goes down. And all this is recorded in the controller, and the tip will move up and move down according to the sample feature. So with this feedback loop, the AFM is able to measure the height of the sample and also the valley of the sample. Okay, so AFM is one of the foremost tools for imaging and measuring material at a nanoscale. So as like I just now mentioned, is the information is gathered by feeling the surface with a mechanical probe. So there's piezoelectric elements in the scanner in the head, which holds the probe. So when it scans, you scan line by line. For example, you scan this first line, followed by second line and third line. Then as it hits a hue, you react because there's a change in the laser position, and the scanner will go up. And as it goes down, the laser position goes down as well, so the scanner will also go down. So you record the changes in the piezo of the scanner, and from this we can construct a 3D profile of the image. So let's look at the magnification scale of the AFM. So for light microscope and SEM, they are for light microscope, the magnification is not that high, tens to thousands. For SEM is a bit higher. So for AFM is one of the highest. It's almost comparable to the TEM in terms of magnification range. So this is an example of a 2D image of the ITO glass. So this is a color scale topography image of a 5 by 5 micron scan. And this color scale tells you that the lighter areas are those which are higher, and the darker areas are lower position. Right, so we can also zoom in to a smaller area, to a 1 by 1 micron. So this is the zoom in image of this ITO glass. Okay, so traditional microscopes, they only measure one way, which is the plane resolution in the plane. And AFM can measure two measures, which is the plane of the measurement and also the direction perpendicular to the surface, which is the in-plane resolution. However, this in-plane resolution, it depends a lot on the geometry of the probe that we use. So in general, the sharper the AFM probe, the higher the resolution of the AFM image. So this is example of the image with using a dial probe. If we're using a probe which is not so sharp. So as it scans along the field, it cannot reach the bottom. So this is the 2D image that you get. However, if you use a very sharp probe, you'll be able to reach the bottom substrate and you can get this profile. Okay. So the tip sharpness is extremely important for accurate roughness measurement and repeatable roughness measurements. Okay, so if over time, if the tip is not sharp, becomes blunt, then your roughness value will be different. So the roughness will also fall as the tip radius becomes larger. All right, so from sharp to blunt tip, and the roughness value will change as well. So it's absolutely important to maintain a tip sharpness for accurate measurements. So these are some of the SEM images of the AFM tips. This one is a normal tip, which we use for normal topography. Then there are some tips which are high aspect ratio tips. These are high aspect ratio tips. These high aspect ratio tips are used for narrow trenches, where the opening of the trench is extremely narrow and the trench is extremely deep. So we have to use special tips for this kind of sample. Right. So let's have a simple comparison for the AFM between the SEM. So SEM and AFM both can measure topography. However, SEM cannot measure the Z direction, the depth. Okay, but AFM can. SEM can measure, is very good for chemical properties, chemical composition. But AFM is good for mechanical properties of the surface. So you can say that SEM and AFM are both complementary and very much required for in an FA lab. Okay, so some examples. So this sample is a wafer sample. And this sapphire wafer has a few very small steps. As you can see from the color differences, it's a very small steps. This is the 3D view, and after flattening, we can do some analysis, doing a line section, and we can see what is the step, depth of the step. 0.3 nanometers, 0.2 nanometers for different steps. Okay, next example is a hard disk media substrate. This is basically our hard disk media. And they measure the roughness for 1x1 micron scan. And this is a 3D view, and they are able to get very low RA and RQ, which stands for average roughness and quantitative roughness. So from this roughness value, we can know that this is a very flat surface and also quite a hard surface. Okay, so this is some basics about the AFM and the normal topography mode. Next, I shall go on some of the advanced modes which are used in the industry for failure analysis and characterization. So one of the most commonly used modes is conductive AFM. As the word conductive, it means we are trying to find whether the surface is conductive or not. So conductive AFM measures the topography and also the electrical properties of the sample at the same time. So how it does that is use a tip which has a conductive coating. So this kind of special probe, they put some layer of platinum or gold or even diamond dope coating on the tip, and they are able to measure the current passing through the surface. And we can apply some voltage on the sample as well. So one example is device circuitry. So this is a common application for failure analysis. So first, these are device circuitry which conduct current. So we are able to get a current image. At the same time, with this height image. From the height image, we cannot tell whether the circuit is bad or not because it's very small circuitry. However, we can zoom in into the scan and we do this conductive AFM scan and we can see which areas are conducting. In this case, for this circuitry, it's passed because there's conductive areas. However, this circuitry is failed because some of the circuits are already open, already gone. Okay, another example is Sram. As you know, Sram, they have this PMOS, NMOS devices. So as usual, conductive AFM, we get topography image, and also we can also find out whether is it a PMOS or NMOS. As you can see, there are different colors. They are darker and lighter colors, and we can also see if the contacts are still present. Okay, so as another mode is scanning capacitance microscopy. So as the name mentions about capacitance, is actually to record so capacitance change between the sample surface and the probe. And as usual, this metal probe is a conductive probe. So in semiconductor manufacturing, we need to identify the dopant profile if there's some failure. Okay. So this SCM is able to provide a quantitative 2D dopant profile as well. So this is example of a field electron transistor FET structure. So we actually use this SCM mode to measure. So from the topography, we are not able to tell much. However, using SCM mode, they will show this SCM amplitude, which shows the dopant concentration. So there are some areas which has a higher concentration, higher dopant, and some which are lower dopant concentration. And the phase channel will tell you whether the dopant type, whether is it the P type, which is the lighter color, or is it an N type, darker area. So this phase and amplitude can tell you about the dopant information. Okay, so another common failure analysis mode is defect measurement. As you know, for surfaces, when you do some sputtering or you do some process on the surface, there may be some defects. You know, so the AFM is a very good tool to measure the defects. Example, in a hard disk media, right? So the defects can be divided into basically a few scratches, but mostly is either a pit or bump. It can be a scratch as well. So most of the time, for example, in a hard disk industry, if there's any defect found in the optical inspection tool, they will get down the coordinates, and these coordinates will be feedback into the AFM coordinates, and then the AFM can go to the area and do a survey scan and also do a zoom in scan to find the defect. So we also have automated tools, automated AFM for this auto defect analysis, where they actually shine a laser on the area, and if there's a defect, it will reflect up as a light, as a bright up area, and the AFM head will go there to scan the area and capture the defect information. So we can capture information like the defect height, depth, or the width of the defect. Okay, so another mode is called deep trench and sidewall analysis. So this is more in the semiconductor industry, where they have this very deep and narrow trench, and other characterization methods, it's difficult to find the depth, especially when the opening is very, very narrow. So this is AFM tip. So it's imaging the trench. This is the profile, 3.7 micron depth, and the tip will remain sharp because of our part system's non-contact mode. Okay. So another example is this dense trench or line width. So for semiconductor samples, they may have different pitch spacing of the trenches and lines. So this AFM is also very good for determining the pitch of this trench line. Okay, so AFM can also measure the sidewall roughness. So this is a sample. There's some undercut, and sometimes we need the roughness information of the sidewall. So with a tilting stage, the AFM can measure the sidewall roughness by tilting the sample in the sideways. So once we get the area, the scan, we can actually use software to rotate it back and to find the sidewall roughness or line edge roughness, line width roughness, etc., etc. Okay, so another mode is magnetic force microscopy. So this mode is actually to check the magnetic force of the surface. So if there's any magnetic domains on your sample surface, this mode will be able to detect as well. So for hard disks, they have some coating, magnetic coating on the surface, right? So the normal topography, we're not able to tell whether is there any magnetic domains. However, with MFM, we can look at the face and we can tell that there's some magnetic domains on this surface. So for failure analysis, they do check whether if there's any missing magnetic domains. And if there's some missing domains, they also want to check whether does it appear on the topography as well. So this will give information on whether this defect happened before the coating or after the magnetic coating. Okay, so these are the MFM images of the hard disk on the different positions. Okay, so in short, there's a lot of modes for AFM. Other than the standard topography imaging, we can also measure chemical properties, magnetic, piezoelectric properties. If your sample has ferroelectric domains, electrical properties, we can measure IV curve. We can also measure mechanical properties like nano indentation. We can also do some nanolithography on the sample surface. We can do force measurements. And AFM can also scan in fluid environment as well. So it's a very versatile tool for research as well as failure analysis. So next, I'll go on to talk a bit about this part system AFM technology. So a bit about our company part systems. So part systems is invented by AFM is invented by Professor C.F. Quote and Dr. Sun Yu Park, which is the founder of Park Systems. Okay, so they actually studied together in this Stanford University, and they came out with this first AFM company in 1988, Park Scientific Instruments. However, now this company has changed the name to the Park Systems Private Limited. Okay. So Park System today, they have more than 300 employees, and we have offices in all over the world. The global HQ is in Korea. So we have offices in Singapore, Europe, China, Mexico, Taiwan, Japan, USA. So over the years, since the invention of the commercial AFM in 1985, Park System has invented many modes, like this non-contact mode in 2004, scanning ion conductance mode in 2009. Okay, and come out with a low noise scanner as well. So some of this technology, which I'm going to talk about, is process illumination. So as you know, most AFM, they use a tube scanner where there's X and Y and Z direction piezo. Okay, but this is not the best AFM. So Park System comes out with a flexure scanner which decouple the Z and XY. So instead of the X and Y and Z are together, they decoupled separately. Okay, and this results in a very accurate surface measurements, right? So this is a tube scanner. There may be bowing effect by the piezo. So even after the software flattening, the image does not look really flat. However, with this decoupled design, we have a very flat scan. Right, so the out of plane motion is very low, very flat scan, very uniform scan. So this is one of the technological advantage of Park Systems. So another technology which I'm going to talk about is this non-contact mode, right? So non-contact mode, which means the tip is barely touching the surface. As a result of this non-contact mode, the tip degradation is very low, and it prolongs the tip lifetime. Okay, so this is tapping mode. The tip is tapping on the surface. However, this will cause the tip to be blown out very fast. So for Park Systems, we have this true non-contact mode where the tip is oscillating and measuring the surface, but it is not really touching the surface. So as a result, your tip can last for many scans. Okay, so let's go on to our line of products. So we do have AFMs for research line and industrial line. So for research, there are different AFMs for different sample sizes. For high vacuum environment, for bio samples, large sample. So from what I know, Mimos will be having this NX20 soon. In a few months' time, it's going to be installed in Mimos soon. And also, we do have AFM for industrial in wafer fabs as well, like this photomask and NX wafer. All these comes with a robot handler for imaging, for scanning the semiconductor wafers. So this is more for the hard disk sample. Okay, so with this, I'm going to show a very short video about the Park System non-contact mode.
Park AFM technology. An atomic force microscope is a device which measures the form and various physical properties of a sample by bringing the tip of a probe to the sample's surface and measuring the interaction forces between the atoms of the tip and those of the sample. Park Systems has built on years of experience to achieve its unrivaled AFM technology, notable for its exceptional accuracy and ease of use. The fundamental technological difference between Park Systems and other companies is in the structure of the scanner, which is the core of an atomic force microscope. The old atomic force microscope design used a tube scanner, which relies on the tube's curvature to alter the relative positions of the probing tip and sample. But this method creates image distortion as the tube curves to the side and warps XYZ measurements. In contrast, the decoupled scanner design developed by Park Systems consists of flexure-based independent X, Y, and Z scanners, so that measured images can be free of distortion and excellent in linearity and orthogonality regardless of scanning range or sample size, and at any scan location or speed. In addition, True Non-Contact Mode AFM showcases a different aspect of Park Systems technology that allows users to perform measurements without any contact between the tip and sample. The tapping mode of other companies measures samples in a way that leads to sample damage and tip blunting, resulting in lowered accuracy. However, AFM measurements with Park Systems' True Non-Contact Mode involves no contact between the tip and sample, thus no sample damage and almost no tip blunting, enabling accurate measurement over many scans and also greatly lowering related tool upkeep costs. In addition, with the development of a high-performance Z detector, which effectively reduces noise, sample surface details smaller than a nanometer can be accurately measured without any creep effects at feature edges. Park Systems builds upon this superb hardware technology with the dedicated operation software Park Smart Scan, making it possible for anyone to obtain optimal AFM images by using the software's auto mode without the need for an experienced operator. A few simple clicks and Park Smart Scan automatically calculates optimum values, making AFM image measurements simple and easy. As we have seen, Park Systems introduces the world to outstanding technologies unmatched in the AFM market and is occupying an unrivaled position as a provider of nano characterization solutions. Park Systems will continue leading the market by staying one step ahead in tech and growing as the world's premier atomic force microscope company.
Okay. So in summary, AFM is widely used in this failure analysis and process monitoring process in this industrial sector. So its relative ease of use and high resolution magnification makes it an excellent tool for surface characterization of materials. Technological advancement in AFM modes like non-contact mode has enabled non-destructive sample analysis. So with this, I will end my presentation and thank you very much for your attention.
The first question is from Jasmine. She says, do you have experience in analyzing glove sample, thin rubber film using AFM? What is the suitable mode for this type of sample, tapping or contact mode?
So for glove samples, if you just want to know, for rubber samples, if you just want to know the topography, you can use either tapping or non-contact mode. However, if you want to know about the Young's modulus, you will have to use the pinpoint mode, which is more like a contact mode, which can give you the mechanical properties like the Young's modulus, the adhesion value of the sample.
Okay, we have another question. How do we know the tip of the cantilever is broken?
All right, so this is a good question. So usually we know the tip is gone when there's some abrupt changes in the measurement result or the image. For example, when you notice the reduction of the image resolution becomes blurry or not clear, or have some repeated pattern on the image, this is result of the tip wear. So if you can see the image, there's some big changes. Most of the time, the tip is wear out.
Okay, I have one last question for you. How do we know the height of every valley on the surface? We need to non-contact mode or tapping mode.
So to measure the height of the surface, both either non-contact and tapping mode can be used. However, non-contact mode is preferred since it can minimize the damages to the tip and sample.
Okay, thank you. Thank you very much, Mr. Brian. I would like to call all our speakers to turn on their camera. Great. Okay, we have one question for Dr. Suhairi. May I know, does Mimos provide AFM analysis?
Okay, we used to have a very old system, AFM system. I think we have decommissioned the system. We are currently expecting a new unit coming to Mimos very soon. So if you can drop Miss Amy an email just to inform your interest about the AFM services. Once the new unit arrives, we will update you accordingly.
Okay, apparently we'll get it sometime in November, I believe. Yeah, that's what someone said. Said. Okay.
All right.
Okay, any more questions from the chat? No, we're going to call it a day. No, I don't see any questions. Okay, that a big thank you to everyone for joining us, especially to our experts in sharing their knowledge. Don't forget to give a thumbs up to our YouTube video and look forward to share more knowledge with you. Kindly email lechme@mimos.my stating a name and organization to get your certificate of attendance for today's workshop. With that, ladies and gentlemen, I'd like to conclude, and I'd like to thank all our speakers. Ladies and gentlemen, goodbye, and till we meet again in another webinar. Bye bye. Take care.
Bye. Thank you very much. Bye.
Thank you.